presentation today. So first, what I want to do is go over the agenda. And this is a brief review. We'll first review the functions and types of filters and filter selection. Then I'm going to go over the conventional, it's called the conventional filter synthesis techniques. And this is in preparation to discuss the advantages of the direct filter synthesis techniques over the conventional techniques. Then I'm going to go and talk about specifically the S-filter, direct filter synthesis tool that's in Agilent Genesys, and follow that with the filter design flow within Agilent Genesys, where you take the synthesis, the filter you synthesized, and you can look at it using Momentum GXF, which is the electromagnetic simulator tool that's built into Genesys, and also SPECTRASYS system architecture tool. And then finally, we will do a summary. We'll go over what we've learned today. So filter functions, probably most of you are aware of all the filter functions, and so I'll just cover this quickly. As you know, they're required in all communications equipment, and they're basic to all RF networks. They limit the signals, and usually the noise is received and transmitted. They help to select information that will be processed and developed, such as in a phase lock loop. And they can direct frequency-dependent energy as in a diplexer. So different types of filters, they're separated typically by frequency. The first type is passive, which encompasses discrete type filters, which are ones made of inductors and capacitors. And then we have crystal filters and SAW, or surface acoustic wave filters, and most of these are usable up to about 1 gigahertz or maybe 2. Then we have hybrid or helical type filters, which are usable a little higher in frequency and are usually used for maybe higher power circuits. But above 1 gigahertz, distributed filters are probably the most common and make up the bulk of applications up to near light frequencies. And included in this category are transmission line, which are like microstrip or strip line, dielectric resonator, and waveguide type filters. And then we have active filters, which are op-amp filters, and they are typically used at low frequency, such as audio or in power supplies. And then finally, digital filters, which include finite impulse response and infinite impulse response, and which are typically used for baseband filtering. And then for filter selection, of course, the frequency band, and sort of what we discussed in the last slide. Performance, insertion loss or Q, rejection, and so forth are typical parameters. And then we have power, which, for high-power transmitter applications, distributed, hybrid, and at low frequencies, sometimes passive circuits are producible up to thousands of watts. And then at the same time, though, the cost increases due to the size and materials that are needed, and so those are considerations in your filter design. So first I want to go over what we mean by the conventional filter synthesis process, because we're going to talk about that and then show how that differs from the direct filter synthesis process. So in the conventional filter design process, you typically start with low-pass filters that are normalized to 1 ohm and 1 radian cutoff, and they have series inductors and henries and shunt capacitors and farads. And these values are usually referred to as prototype or G values. This low-pass then serves as a prototype for designing specific low-pass filters with other cutoff frequencies and termination resistances. And so the specific low-pass filters are usually found just by scaling the G values, for your desired resistance and cutoff frequency. And then bandpass filters are designed by transforming and scaling the low-pass prototype. And so with a conventional bandpass transform, each low-pass prototype series inductor transforms into a series inductor and a series capacitor. and each prototype shunt capacitor transforms into a shunt inductor and a shunt capacitor. And so, therefore, the bandpass has twice as many reactive elements as the low-pass prototype. So the conventional filter synthesis tools, Agilent EEsof has a number of conventional filter synthesis tools, and these include what we call the passive filter synthesis, or sometimes referred to as the LC filter synthesis tool that resides in Genesys, and this is for your standard LC type filter. And then we have a distributed filter synthesis tool called mFilter that's also in Genesys, and it's for designing your distributed filters, sort of such as Microstrip, strip line, and it can also synthesize cavity filters such as this comb line round rod that we have shown to the right. And then we have an active filter synthesis tool in Genesys called EEfilter, and then finally a digital filter synthesis tool, which is, it's in another tool. It doesn't reside in Genesys. It's in a tool we have called System View, and it's strictly a system design tool. It has a tool called Digital Filter Designer that is used for designing FIR and IIR type filters. So with the conventional filter synthesis tools in Genesys, we're going to focus on those, the analog synthesis tools. It's pretty much the same flow no matter which one of the three synthesis tools you're using. The properties window has 5 tabs, and you can see the tabs across the top of each of the synthesis tools shown here. This is filter, this is EEfilter, and then this is mFilter. So we have a topology tab, a settings tab, a defaults or options tab, G-values, and then a summary. And I'm going to show each one of these and how the process of the flow is within the conventional synthesis tools. So I'm going to use the LC or passive filter synthesis tool to show you what the conventional flow is. You typically start from the leftmost tab and work your way to the right. The topology tab is where you select the type of filter, which can be low pass, band pass, high pass, or band stop. And then you can select the shape, and we show all the shape selections here for the band pass filter, Chevy Chev, Bessel, Butterworth type. And then you select the subtype, and there's a number of different subtypes, which are different configurations that sometimes are affected by the settings on the settings tab. Depending on if you have like a wide band or narrow band filter, you might need a specific type to make it realizable. And there's also, you can synthesize differential or balance circuits. So this shows a few of the topologies that are available for our bandpass filter in the LC filter synthesis tool. There are over 20 types of, these are the subtypes that are available, and there's over 20 types for a bandpass filter. So then the next tab is the settings tab, and the settings tab varies slightly depending on the selections on the topology tab, but basically it's where you enter cutoff frequencies, input and output impedances, order, attenuation, and for a Chevy Chev filter you would enter ripple. And this tab also has an estimate order button, so if you select this button, it opens another window where you can enter in specific frequencies and the attenuation at each of those frequencies. And when you enter those in, down at the bottom, it will display a required order, or the order it will require for you to achieve that attenuation at each of those frequencies. The next tab is the defaults tab, and this is where you specify the Q for the inductors and capacitors. As you can see on the left, we have here the specified infinite Q, or very high, almost infinite Q for the inductors and capacitors, and so you see very little loss. And then if you specify a realistic Q, such as 50 or for an inductor, 100 for a capacitor, you can see that it takes into account the loss in the filter. Now, what this does is when you synthesize the filter, it will input these Qs into each of the components in the schematic, but after you're through with the synthesis tool, you can go in and easily change the Q to another value. And the last two tabs in the conventional LC filter synthesis tool is the G-value tab and the summary tab. The G-value tab is for what filter does. LC filter directly computes the low-pass prototype values, or G values, for popular response shapes, and it doesn't use tables, so any passband ripple greater than 0 and less than 3 dB may be chosen. And this is true even for elliptic filters. So the G values calculated for the currently selected filter design are shown in this G values tab. The summary tab it shows the summation of the G values, and this quantity can be used to estimate the filter insertion loss and group delay for the filter if frequencies well removed from the cutoff. So as we've seen, the conventional filter synthesis technique involves fitting pre-existing schematic to the user's design criteria. And over the years, hundreds of designs have been calculated, and these designs can be frequency and impedance scaled to fit many different design scenarios. So usually this works pretty well for most applications. But this puts a limit on the shape of the filter. So you're limited to shapes such as conventional shapes, such as Butterworth, Chebyshev, and so forth, as we saw before. Here we have a third-order 70 megahertz IF filter, where you can see we've entered from low cutoff of 55, upper cutoff of 85, and we've designed it using the conventional technique, and you can see the response. We'll compare this to the direct synthesis technique for designing a similar type filter. So S-filter synthesis tool is included in Agilent Genesys, and it's the 5th filter synthesis tool that's available. It uses a technique called direct synthesis that allows for non-conventional designs, and contrary to the lookup approach described before, direct synthesis takes the user's design criteria and forms a mathematical representation, or is normally known as a transfer function, and extracts a schematic. So you can, with this technique, more economical and effective filters can be designed by controlling the location of the transmission zeros. So what do we mean by transmission zeros? Well, transmission zeros occur at frequencies of infinite attenuation or no signal transmission. So all pole filters, such as Butterworth and Chebyshev, have transmission zeros at infinite frequency for low-pass filters, at DC for high-pass filters, or at both DC and infinity for bandpass filters. So elliptic filters have finite frequency zeros in the stop band. And if we look a little deeper as to describe what do we mean by a transmission zero, so if you look at a DC transmission zero, this can be represented by a series capacitor or a shunt inductor. And so you can see the DC will be blocked by the series capacitor, and the shunt inductor will short DC to ground. Similarly, the transmission zero at infinity is a series inductor and a shunt capacitor. And then finite frequency transmission zeros are either series LC or shunt LC circuits. So let's look at an example of the conventional filter synthesis, and as when we're talking about zeros. You can see at the top right here we have the third order bandpass filter, similar to what we were talking about. And in B, we have this is the 3 transmission zeros at DC, And you can see the effect. This shows the effect. The inductor, the series inductor, basically disappears, as does the shunt capacitors. And then at the bottom, we have the 3 transmission zeros at DC. So, at infinity. And so at infinity, the series capacitor and the shunt inductor basically disappear. So if you look at the whole bandpass filter, which is shown at the left, the conventional all-pole bandpass filter has an equal number of transmission zeros at DC and infinite frequency. So a third-order bandpass filter, as we show here, has 3 transmission zeros at DC and 3 at infinity. So the conventional approach usually works well, unless an engineer needs a slightly different topology than the existing ones, like we talked about, the Chevy, Chev, and Butterworth. So, what if you need a symmetric response, or you need to notch out an unwanted frequency? Well, increasing the order, as we've shown here, from a third order to a seventh order, this increases the attenuation above and below the pass band. So, in the past, engineers would often take a pre-existing design and add some elements to it and launch an optimizer to recover the desired response. And this takes more time and more effort. So if you want to achieve, say, a symmetrical response, this isn't really possible easily with a conventional filter synthesis tool. And also selective notching, if you want to notch out an interferer or some other frequency, that's also difficult with a conventional filter synthesis tool. So LC filter offers a rich set of topologies, better than most on the market, and so LC filter is a very good tool if the standard filter topologies satisfy your requirements or your design objectives. But the procedures used by conventional synthesis tools don't find all of the available topologies either. In fact, there's 226 unique realizations for the 6 transmission zeros that we showed, where you have 3 at DC and 3 at infinity. And there's many more if you want to select or put the transmission zeros at other locations, such as 1 at DC and 3 at infinity and 2 finite zeros. So S-Filter program synthesizes all available topologies by extracting the zeros in every possible sequence. It also allows the user to specify DC, infinite, and finite zeros completely independently. So this has many benefits, and you can sometimes improve component value ratios. It allows you independent control of the rejection above and below the pass band, and it allows you to place notches at desired frequencies. And you can design with unequal terminations. So let's look at the direct filter process as contrasted to the conventional filter process. So here's the S-Filter window, and first thing you can notice is that the tabs are totally different than we had in the conventional synthesis tools. The first tab is the Start tab, and you don't have to start here. You can start on the Specifications tab, but it's sometimes helpful because this helps you to start a new filter, start from a blank. And you can also save your filter here or load an existing filter from here. But another helpful tool on the Start tab is the Shape Wizard. And what this allows you to do is to start with a conventional shape that maybe you're more familiar with. And so when you press the Shape Wizard button, it opens this window where you have a selection similar to the Specifications tab, on the typical conventional tool, where you select a Butterworth, Chevy, Chev, or elliptic, low pass, high pass, or band pass, and then you enter in the order and the pass band and the ripple or attenuation. So what I'm going to do is start with the same filter that we designed or synthesized in LC filter. I'm going to start with that in S filter. So the next tab in S-Filter is the Specifications tab. And this is where the direct filter design process begins. So if you use the filter wizard on the Start tab, the filter parameters will be entered for you and the response will be shown. So the top part of the Specifications tab is similar to the Settings tab in the conventional synthesis tools, where you have source and load, and you can specify those independently. Then you specify the passband requirements, and like I said, they were already entered here because I used the wizard. Then you select the type, and then also whether the shape is maximally flat or equal ripple. You can also design either lumped or distributed filters, and for this example, for comparison to the conventional tool, I'm going to design a lumped element filter. And you can specify the capacitor Q and the inductor Q, as we have here with 1,000 for the capacitor and 200 for the inductor Q. And then lastly, the quarter wave frequency is strictly for distributed filters, and this is a way of defining the reentry point of your distributed filter, which does not have, you don't have that in a lumped element filter. So then the last thing we want to do is, you notice that we didn't have the order up here. Instead, because we used the wizard and we specified a third order filter, it put 3 zeros at DC and 3 zeros at infinity. And that's, so we basically got the same shape response, asymmetric shape, that we got with the LC filter synthesis tool. So let's see how we can use direct synthesis to modify our design. So for example, S-Filter allows the engineer to place a different number of zeros at DC and infinity. And if the number of transmission zeros at infinity is 3 times the number at DC, then the response can be symmetric, which we define symmetric as equal roll-off above and below the pass band. So the conventional bandpass has too few zeros at infinity in relation to the number at DC, and too little selectivity above the pass band to be symmetric. So here we've defined 6 zeros at infinity and 2 at DC, which is a 3-to-1 ratio, and this results in our symmetric response of S21 and also of group delay. So S-Filter allows placement of zeros at finite frequencies as well, which then can be tuned to obtain the desired response. Finite zeros can be used to increase attenuation or notch out spurs or interferes or any other unwanted frequencies. So as you can see here, we've specified a 0 at about 37 megahertz and then another at about 102 megahertz. And so we have a little bit more roll-off above and below the pass band, but we've retained our symmetric shape for our filter. And this allows me to, I can tune these with the arrow buttons or with the keyboard or mouse wheel. You can tune these zeros up and down to achieve the exact response that you're looking for. So the next tab is the Extractions tab. So far, we have specified our filter and designed it for the exact response we're looking for. We haven't really talked about the schematic yet, because with S-Filter, it's a little different. You actually custom design your filter for the response that you need. So in the Extraction tab, a filter is, the transfer function. I told you earlier that a S-Filter uses a transfer function, and a transfer function can be represented as a ratio of sums of products or a ratio of products of sums. So using the products of sums representation, the equivalent filter network can be obtained extracting one product at a time, where each successive product represents some combination of circuit elements. And this results in multiple schematics that are possible with the exact same response. So the previous design, as we've shown here, results in 58 unique schematics. So it's as you see here, it shows that we have 120 permutations or different schematics where there's 29 of them unique. But that's using a series element first. If we uncheck the series element, we have a parallel or shunt element first, and we get another 29 unique solutions for a total of 58 unique solutions. So, and the schematics are placed in a table for easy sorting, and you can see the headers across the top we have are number of capacitors, number of inductors, the inductor ratio, and the permutation order is the order in which the zeros are extracted. So if you select or click on the header in the table, it sorts that by that column, and what we've done is sorted by the inductor ratio to have the minimum inductor ratio, and in that way we can use the minimum number of, or we can use the same types of inductor, and they'll be close in value. So the table is also customizable for the headers across the top are customizable, and if you select Customize Table button, it opens up a new window where it shows everything that's available to place in the header of the table, and then you just use the arrow buttons to put it in the right-hand window, which is what's shown in the table, and there's a number of selections for both LC and distributed type filters. So as we've shown, the number of capacitors, inductors, ratio, and permutation order are what are shown in the top of our table. Also on the Extractions tab is you can customize your table a little bit more if you need to go a little more detail. There's an Edit Goals button, which allows you to define your extraction goals if you want to control any of the measurements that are shown here, such as capacitance or inductance or the ratios. I've selected inductance to be less than 200 nanohenries, and that will limit my values or limit my ratios based on what I define in my goals window. Additionally, on the Extractions tab, like I said, S-Filter will extract a certain number of unique solutions that are identical. So the response, the schematic is different, but the responses are identical. Well, there is a selection that allows for inexact responses, and these are responses that are going to be very similar to our exact ones, but maybe a little bit different. But as you can see here, it increases the number of unique solutions found. It went from 58 to a total of 160. And if you select the inexact, a lot of times you can optimize the inexact schematics to make them a little closer to what you are looking for, the exact response you're looking for. And many of the inexact might have fewer parts and more favorable topologies. But just so that you don't get them mixed up, we highlight the inexact solutions in red in the table, and the exact solutions are in white. So now that we have the schematic, we can transform the tab, the schematic even more to try to make the schematic more. There's options that that we might be able to transform it to reduce the number of inductors or capacitors, and this is called the Transforms tab. Includes many different transformation tools, and it many times helps you to improve the realizability of the filters. So on the Transforms tab, this includes basic operations such as splitting and combining elements and pi to t and t to pi transforms. And then we also have lump to distributed, which is LC to transmission line, and distributed to lumped, which is the reverse. And in the window, it shows the selections at the top, and the diagrams at the bottom show before the transform and after the transform is applied. The inexact transforms, which would be, well, for example, an LC to transmission line is not going to be a direct transformation, of course, so the inexact transforms are highlighted in red. So additional transforms on the Transform tab are what we call compound operations, which is finding a dual of a schematic. Equate all L's and C's, which means that it can make all of the inductors the same value or all of the capacitors the same value. There's Norton transforms, Kuroda transforms, couple lines, T lines, and there's many more, too many to really go over in this presentation. But a lot of the transforms are discussed in a very good book called HF Filter Design and Computer Simulation by Randall W. Ray. And this is actually available with Genesys in a PDF format. So if you've purchased Genesys or you get an evaluation copy, you can look at this book in PDF format and examine some of the transforms that are available in an S filter. So for an example of the Transforms tab, I would like to show what I mentioned before was the Equate All L transform, and we'll apply that to the previous design. So on the left, bottom left is before the transform, we actually have 3 inductor values. So the first and last inductor are about 298 nanohenries. The shunt inductor is 524, and the other series inductor is 670 nanohenries, which results in 3 inductor values. So we select Equate All L's and apply selection, and it transforms our schematic to design that all of the inductors, all 4 of the inductors are now the same value. They're all 298 nanohenries. What this does is it reduces the number of unique inductors to only 1 that you must design and model and purchase and test and stock and pick for assembly. So it can save many costs all along the way of your whole design and manufacturing process. Now the design on the right that has the equal inductors does have 2 more capacitors, but in many cases to have just 1 inductor, which are usually more expensive than the capacitors, it might be a very good trade-off to trade off 1 inductor value for 2 extra capacitors. And then finally, the last tab in the process of S-filter is the History tab. And the History tab keeps track of all of the transforms that have been applied. Because when you start down a path using transforms to modify a filter, occasionally you might need to back up a few steps. Maybe you've applied a transform in error and you just didn't get the design that you wanted. So what you can do is go to this History tab and delete any of the transforms that you've applied, or back up to any step in your transformation process. So this completes the synthesis process of the filter using S-filter. You know, the response has been tailored to exactly what we were looking for. We have the best available schematic was selected and modified to reduce the cost and improve manufacturability. And so the synthesis modules in Genesys, usually this is an iterative process till you get the schematic that you want. And the synthesis tools will give you a schematic, a linear analysis, and sometimes a layout, and then also a graph. And then, you know, after it's completed with the synthesis process, the schematic's yours to modify, optimize, and include in other designs. So the question sometimes, though, is, you know, how accurate is the synthesized circuit? Well, in many cases, it's accurate for many designs, you know, especially at low frequencies. However, we'll now examine ways to improve the accuracy of our design using the other tools in Genesys. So here's a representation of the complete Genesys integrated suite. Included in the Genesys suite is a SPECTRASYS RF architecture design tool, the synthesis capability we discussed, circuit design, which includes linear and nonlinear circuit simulation, PCB layout tool, and an electromagnetic simulator, and then export capability and import capability so that you can bring in your measured data and compare it at any level. So far all we've looked at is this synthesis block here. So what we'll look at now is how we can improve our design using the other tools within Genesys. So one thing you can do is that's easily done is just to add microstrip lines or strip line or whatever kind of connecting lines that you're using to your schematic, and also the lines and via holes and any kind of connecting lines. You can also enter in the substrate material. We have substrate libraries for GE, Rogers, and Taconic, and this will increase the accuracy of your schematic representation of your filter design. A next step that you can do is to replace the ideal models that we've used. Well, not replace the ideal, but I mean that the original values that were synthesized were often fractional sizes, which aren't available or readily available. And so we have in the tune window within Genesys, you can select a standard value, and then you select the tolerance, which here we have specified 5%, and then you can tune all of your components to the standard value of whatever tolerance you select. And in many cases, optimization might improve the response, but this selection is dependent on whatever tolerance, the standard value that's selected here depends on whatever tolerance you have selected at the top. With a 5% tolerance, we were able to set all of the parts on standard values and still maintain our symmetric response very close to what the response was before we set it on standard values. The next step is other model options. So what we can do is we usually start out with standard capacitors and inductors with Q. You can add built-in models that we have in Genesys, which include more parasitics, as shown here. You can use vendor models that are available. We have many vendor models that are included with Genesys. You can create your own custom models. It's very easy to create custom models. And you can use measured data, like S-parameter data, for any of your models. So you have a number of different ways to change the model and improve your accuracy of your design. Now, there's only one caveat here, is that, or I should say a warning, is that if you're going to be using one of the vendor libraries or an S-parameter file, maybe measured data, you need to ensure that the substrate material and the substrate thickness, pad size, component orientation, and everything matches the actual design layout that you are going to use. Otherwise, your accuracy may actually suffer instead of improve if you don't make sure that the models that you're using match your filter design. So the next step would be to create a layout of our filter, and we can do that within Genesys. And pads are added for connecting the components together. And the pad capacitance and coupling between pads and interconnecting lines can many times add problems of their own. So depending on the component values, a few tenths of a picofarad may or may not influence the filter's response. But the ability to view these effects is not possible at the schematic level, and what you have to do is you have to use an electromagnetic simulator. So integrated in with the Genesys tool is Momentum GXF, which we used for our electromagnetic simulation. Now, there's a unique capability within Momentum within Genesys is the co-simulation capability. When you're using discrete elements, trying to do an EM simulation in most tools can be very difficult because you have to place the ports manually on the layout, and then you have to import that in EM simulation results into your schematic to include it in the schematic. But Genesys is actually, the co-simulation capability does not require placing ports on the layout. The ports are associated with the footprints that are automatically placed on the layout. You just define the footprints in the schematic, and they're automatically placed, and the ports are associated with them, as we show in the 3D view here. You can see it identifies all the ports that are associated with the footprints. These were not manually placed. Genesys did this automatically. So then you can run the simulation. You don't have to use a lookalike or anything to combine the two simulations. So the next step is design for manufacturability. We need to make sure that we can build it and that we're going to get good yield in manufacturing. And so included is Monte Carlo analysis and yield analysis in Genesys. And we can run Monte Carlo and yield analysis to determine what our required final tolerance will be and what the final cost will be. As you know, higher tolerance parts are usually more expensive. So now that we've completed our filter, we have a nice, very accurate simulation and design. We've designed our filter to the specifications, but how will our filter perform in our system? So SPECTRASYS system architecture tool is also integrated into Genesys with S-filter and Momentum. And typically the system architecture is created first, and the filter parameters flow down from the system requirements. We usually use behavioral models, as shown here, and to determine the system performance. And then the filter design, we can take the filter design and substitute it in after we've completed the filter design at the system level and determine that we're still meeting our system specs. So SPECTRASYS has a lot of capability to display full spectrums at any node in the circuit. So here we can see our filter passband is displayed. And it also shows over here, though, some leakage from our second LO. It shows, actually it's called LO3, and it's at 175 megahertz, about minus 96 dBm. And it shows us that LO3 and then the whole path through our bandpass filter, and it shows up as a spectrum in our spectrum plot. Now, this LO leakage is pretty far removed from our passband, and it's fairly low value, so it may or may not be a problem. But if it is a problem, at least we've identified it, and we can redesign our filter and maybe put a notch in there, which S-filter, as we've said, has allowed you to put a notch in there to notch that out. So also with SPECTRASYS, you can look at cascaded paths, or what we call level diagrams. And at the top here, you can see I'm displaying what we're looking at is this path through the circuit. But you can look at paths both forward and backward through in SPECTRASYS. And the path is displayed at the bottom of our graph and shows every component and every node in the path. And here's our filter that we designed. And we're displaying power and noise power on the left and noise figure on the right. SPECTRASYS can also display tables. So if you prefer tabular data, a lot of people are used to spreadsheets and like to look at it in tabular data. It can show it in tabular data, which can be exported to a spreadsheet as well. And it's very easy to look at this or any of the diagrams I've showed you, that either the spectrum or the paths or the tables, by just right-clicking on the output node of your circuit, and it immediately displays any of the graphs or tables I've shown you. So in summary, what we've talked about today and what we've learned is that S-filter, with S-filter, engineers are able to directly synthesize multiple solutions for low-pass, high-pass, and bandpass filters. We can asymmetrically place DC and infinite zeros to increase high or low side selectivity or for response symmetry. Place and tune finite zeros for increased selectivity where needed and or to notch out unwanted frequencies. We can select and transform schematics to obtain the best possible design and improve manufacturability. We can also use momentum GXF EM simulation combined with enhanced models to ensure first-pass success. We can perform statistical and swept analysis to ensure that everything is manufacturable, and we can integrate it at the system level to ensure that our design will continue to meet system specifications. So thank you very much for attending the Genesys Direct Filter Synthesis Seminar. Genesys offers the industry's widest coverage of 11 RF and microwave circuit synthesis capabilities. You can test drive them in Genesys to personally experience how your design productivity can increase by orders of magnitude. The latest Genesys 2010 also comes with breakthrough X parameters nonlinear simulation technology and a 10x optimization speedup and significant reliability improvements. So just Google Agilent Genesys for more information or for your own evaluation. And back to you, Carmina.
Thanks so much, Rick. Okay, in a moment, we'll begin today's question and answer segment, and remember to complete the survey that will automatically launch at the end of the webcast. And as I mentioned at the beginning, by submitting the survey, you'll be providing us with valuable information on how we can offer you more and better webcasts in the future. So please take a moment to do that. Okay, now onto the question and answer portion of the event. Just a reminder, if you have a question, simply type your question in the chat window and select all panelists in the drop-down menu. We'll try to answer everyone's questions live, but if we run out of time, we'll respond to the remaining questions via email. All right, Rick, here's your first question. This is from Liam. This program looks a lot like the old EagleWare software.
Yes, you should recognize it. EagleWare was started back in about 1985, and in 2005, Agilent purchased EagleWare, and with that, the Genesys software. But Agilent has continued to improve the software. One thing they've done, which is a great addition, is the Momentum GXF, which is the momentum engine, same momentum engine that's in ADS, which has 15 years of proven, accuracy and capability. And that was integrated into Genesys a few years ago, and we're continuing to improve it, things like S-Filter and some other tools. So yes, it is the same tool.
Great, thanks. Here's your next question from Scott. What version of Genesys is this filter synthesis wizard available?
Well, the latest version is Genesys 2010.05, but it's available in Genesys 2010. And we will be coming out with a new version, Genesys 2011, which will be at the IMS MTT show. We'll display that, and the final release will be in August.
Okay, very good. And don't forget, we'll be at IMS 2011, and our booth is number 813. Okay, so here's a question from Les. Are these filter design tools available in ADS? Did we already answer that?
No, I don't think I answered it yet.
Go ahead.
Yes, they are available in ADS. What you would do is you would use the same interface that I showed you. You would complete your synthesis of your filter and the system capability, all the capability there, and then you can export that to ADS. We have export capability, and it pulls it over, including the analysis, which turns into a test bench, in ADS, and displays it in ADS. And so then you can use all the capability in ADS on your filter.
Okay, very good. Here's a question from Andrea. Does S-Filter Direct Synthesis replace the other filter synthesis tools in Genesys, such as M-Filter?
No. It's, as I showed earlier in one of the first slides, M-Filter, LC Filter, A-Filter, they are all still in Genesys. It doesn't replace it. The other tools are, like I said, are the conventional filter synthesis tools. So if you're designing a standard Butterworth Chebyshev filter, that type of filter, those are still very good tools to use and have a lot of capability. It's just that S-filter expands this capability and allows you to design more custom type responses.
Okay, here is a question from Andre. This wasn't discussed in this webcast, but can someone provide guidance regarding implementing and realizing digital filters?
Well, I touched on it at the very beginning. The digital filter designer is in our other tool called System View, and that's spelled SYSTEMVUE. So if you Google Agilent System View, then you would get information on an evaluation copy of that as well. So you can evaluate System View along with Genesys. And what's nice is they're built on the same platform, so they look very similar, although the capabilities are very different because you're in the digital world versus the analog world. But there is a digital filter designer tool built into System View for that capability.
Hey, thanks. A question from Dan. How can you choose different input and output impedances for the filters when the impedances are different from each other?
Well, that was on the specifications tab back a little ways. There, on the specification tab, there is input impedance and output impedance, and those are, you can select those individually.
Okay, and a question from Tim. Can you specify all transmission zeros at finite frequencies? For example, no transmission zeros at DC or infinite frequency.
Yeah. Yes, you can. As I showed before, what I had before was 1 at DC and 3 at infinity, and then 2 finite zeros. But you could specify the finite zeros separately. Yes.
Okay, and here's a question from John. Is S-filter a new feature? I haven't used Genesys for a while.
It's fairly new. It's not it's not brand new. We had a version of it out, but it's fairly new. Yes.
Okay, and a question from Tim. Do you have tools for direct synthesis of multiplexers with arbitrary responses for each filter?
I've never used S-filter design a multiplexer. I would think you would typically, when you design a diplexer or multiplexer, I've only used the filter synthesis tool, which what you usually normally do is design say a low pass or each individual filter pass band separately and design it as singly terminated. And then if you design it as singly terminated and connect them back together, then then you can have your diplexer or multiplexer.
Okay, and a question from Will. How is a band reject filter created using S-filter?
Well, it's not one of the standard selections. Band pass, band stop is not a standard selection, but what you would do is you would typically just put a notch in wherever you needed attenuation. So, but it's not one of the standard synthesis selections. You would just place a notch wherever you needed the attenuation.
Hey, Rick, and here is one of our last questions from Fierus. Can we do active filter design as well with Genesys?
Yes, it's not S-filter, but that was the other tool that I showed. It's called A-filter, and that was in the beginning as well. And if you purchase Genesys or evaluate it, what we have is a number of synthesis tools, and the filter synthesis tools are all usually grouped together. So if you buy one, you purchase them all in the filter synthesis tools. So an A-filter is one of them. Yes.
Okay, and one last question from Joseph. Has the design of an actual filter using this tool set been validated against measurement?
Yes. The synthesis capability is unique in Genesys, but all of the simulation capability that we have of the actual design and everything is done by our linear simulators and our electromagnetic simulators and everything. And yes, we do have many comparisons of simulated versus measured data.
Okay, Rick, I think that's all the questions we have for today. A great interactive audience today. I'd like to get some closing comments from you.
Well, I'd like to just thank everybody for attending. I appreciate you taking time out of your day to attend. And again, if if you'd like an evaluation of Genesys, Google Agilent Genesys, and if you want an evaluation of System View, as I described, it'd be Google Agilent System View. And also, or you can talk to your local Agilent EEsof representative. If you're familiar with who that is, I'm sure they can provide you with an evaluation as well.
Great. Thanks so much, Rick, and thanks for your presentation today.
Okay. Thank you, Comarina.
Sure. As we wrap up today's presentation, remember that we will email you a link when the on-demand version and the PDF slides are posted on our website. You're also invited to register for our next webcast, LTE Advanced, Overcoming Design Challenges for 4G PHY Architectures. This is our 10th webcast in the Innovations in EDA webcast series brought to you by Agilent Technologies. If you're viewing the on-demand version of this webcast and have a question about any of the material, please email Rick directly at richard_carter@agilent.com. I'd also like to remind on-demand viewers to complete the webcast survey that will automatically launch at the end of the webcast. Thank you again for attending today's event, Direct Filter Synthesis for Customized Response, brought to you by Agilent EEsof. Copyright of the presentation materials is owned by Agilent Technologies. For a current schedule of live and on-demand events, please visit us at www.agilent.com/find/events, and you can use the URLs on the screen for a look at our recorded webcast. I'm Carmina. Thank you for joining us, and have a great day.